Okay, now it's 4+2. Because there are two students are joining, we wait a little bit. We start. Today there are 4 tasks to do. The first one is a beam stiffness derivation. Although it's not original problem from the questions, but I prefer to help you to repeat the derivation for that. The original material for this part you can find in the model. There is one is equivalent stiffness for frame. And then the derivation detail is this document. Okay. It is distinguished to statically determinate structure and statically indeterminate structure. So if it's statically determinate structure, for sure we can get the bending moment for the whole structure, which is mbx. And for statically indeterminate structure, we can know the distributed load. So let's I give one example, and then we can try to repeat the solution for task 1. Stiffness for beam. Let's find one statically determinate structure. Let's assume there's one simple supported beam. And we want to find the relationship between F and U. So the relationship between F and U should be F equals to KU. As long as we get the stiffness for beam, and then we can combine it together with spring or other components, then we can get the equivalent stiffness for the whole structure. And now let's try to find K and U for this beam. It's pretty easy. We can pretty clear about the bending moment from this X. The bending moment mx is equals to half f times x when x is greater than 0 and lower than half L. Okay, the original equation we are going to use is EI v second order is equal to minus mx. V is the displacement. Okay. And then if we make integration of this equation, we get EI v first order of derivation should be equal to minus 4 above f x squared plus c1. C is one of the constant. Continually, we make the integration. We got that's the final expression for V, the displacement expression. And now, because there are two unknowns, which is C1 and C2, these two constant, we need to determine these two values depending on the boundary condition. Because we have two unknowns, C1 and C2. At least we need two boundary conditions to determine these two values. The first one is when x is equal to 0, v is equal to 0. At this point, x is equal to 0, v is equal to 0. Okay. If we substitute this boundary condition in equation 3, we get C2 is equal to 0. Then we need another equation to determine C1. So for sure, we know because this problem is symmetric at the middle of the span, when x is equal to half L, the v prime should be equal to 0. The slope of the deformation should be equal to 0. Then we get when x is equal to half L, v prime is equal to 0. Then we substitute that in equation 2. We got minus 16fL squared plus C1 is equal to 0. Then we get C1 is equal to fL squared divided by 16. Okay, and then we make the final expression for EIVX. It should be equal to minus fx cubed plus fL squared divided by 16 times x. That's the final solution for Vx. Then we know that u is equal to v when x is equal to half L. Substitute that inside. EIV EIU is equal to minus EIU equals to FL cubed divided by 18. And then U times 14 EI divided by L cubed is equal to F. Then this is K for this simple supported beam. Is that clear? Or any part is not clear, you can ask question and we can explain a little bit. The derivation is pretty important. I hope you can know how to derive that. And for sure, maybe you have another method such as principle of virtual work or something like that to derive the relationship between F and U. It depends on you, but Sasha provided this method. If you can understand this one, is very, very good. Any question on this one? we want to derive the stiffness for this simple supported beam. Because in the lecture, it only gives us 2 tabs. It only gives us 2 tabs, but for others, you are required to derive by. That's what I'm doing. We derive the stiffness for this simple supported beam. No question? Okay, if you have no question, after this tutorial, you can practice this one. You can practice this one by yourself. The boundary condition here is when x is equal to 0, you get v is equal to 0. When x is equal to 0, the slope is also equal to 0. And here, when x is equal to half L, okay, if you have no question, let's continue for question for this second task. Free vibration for undamped system. Let's check the equation table. This equation table is pretty useful. During this tutorial, I will always follow this equation table and set the correspondence between the question and this equation table. Last week, we explained how to get the equation of motion for SDOF system, is this one. As long as we get the mass, the damping coefficient, and the stiffness, and then we can get the equation of motion. And today we are going to talk about the free vibration of the SDOF. It means we need to get the expression for this equation. So for undamped system, it means C is equal to 0. So the equation of motion tends to be mu double dot plus ku equals to 0. So you are not required to solve this problem, but the expression for that ut is equal to a cosine omega nt plus b sine omega nt, in which a is equal to u0, b is equal to u0 dot divided by omega n. U0 is the initial displacement. U0 dot is the initial velocity when t is equal to 0, when t is equal to 0. Okay. And omega n, it is the natural circular frequency. It is equal to the square root of k divided by m. Its units is right per second. For sure, after we get the natural circular frequency, we know that for one vibration period Tn, it is equal to 2 pi divided by mn. It is natural period. And the frequency is 1 divided by Tn, or omega n divided by 2 pi. It's natural frequency. That's all the useful equations we are going to use. Okay, let me draw the finger of the solution. Okay, that is T, that is U. Some feature points we need to emphasize. At the beginning, the magnitude is U0. And the initial slope is U0 dot. Okay, and then the period, it is the time for one entire vibration circle. The time for one entire vibration circle, it is a natural period. It is Tn. Okay, and then the magnitude for the vibration. Because it is undamped system, so it means the magnitude during this whole vibration, it keeps constant. It keeps constant. The value, it is a squared plus b squared, the square root of them. A and b has been expressed above. That's all the information we need. So remember, if you're doing one quiz or in the final, you are required to draw the finger for the displacement history. And every people knows that should be one harmonic, but you need to give some feature point. The first one, U0. The second one, U0 dot. Third one, Tn. Fourth one, the magnitude. You should express that pretty clear. Then you can know what the expression it is. What it looks it is. Okay, let's check question 10 or question 11. Let's check question 11. The problem is one single degree of freedom system, and the displacement towards to left is positive. So there is one bullet shooting on this car, and because of this effect, there will be one initial velocity. Then all we need to do is, because we know the expression for this system is this one, so the ut should be equal to a cosine omega nt plus b sine omega nt. we just need to determine u0 and u0 dot. As long as we determine u0 and u0 dot, then the value for A and B we can obtain. For sure, because before the vibration start, the car remains at one balanced position, so u0 should be equal to 0. And suddenly, when we have one bullet shooting on this car, and there is one initial velocity, that is what we need to calculate. Okay, and now let's try to get the mass and the spring. The wooden block, it has 5 Newton weight. The bullet has 0.025 Newton, and the speed is VO. Let's try to question 11. We know that for the block, I'm not. For the wooden, we call that MO. It has the mass for that is this value. For the bullet, and because of the conservation, MB times V0 should be equals to MO plus MB times U0 dot. Because of this bullet shooting on that, it will provide the whole system one initial velocity. The initial velocity is U0 dot. So U0 dot should be equals to MB divided by MO plus MB times VO should be equal to 0.025 divided by 5.025 times 20. Let me check the result. 0.055995 meter divided by second. That's the initial velocity. We know that the initial displacement is equal to 0. And the mass for this system is equal to 5.025. And the stiffness for that is equal to, check the system, equals to 20. And for sure, the final expression for this vibration should be equal to let's check omega n. So this should be equal to U0 cosine omega nt plus U0 dot divided by omega n sine omega nt. And then this is equal to 0. This is equal to 0.0995. This is equal to this one. Finally, That's the final expression for this displacement history. And now, if we want to draw the initial displacement is 0, the initial velocity is equal to 0.0159. Okay, and the time for Tn, this is for one entire period. Tn is equal to 2 pi divided by omega n is similar is 1.01 second. So this is equal to 1.1 second. And the magnitude zero point 0.0159. Okay, that's all. Any problem? Any problem for question 11? Basically, it's pretty easy. All you need to do we always need to do all the diagram as n? No. This question, it only requires us to calculate the expression, but I prefer to draw that. In the quiz, it maybe requires you need to ask the description of the question. If it's asked you to do, you need to do. If not, then it's not necessary. The initial weight should be 0. Oh yeah. Sorry. Yeah, the initial velocity should be 0.0995. 0.0995. It means the initial slope is equal to 0.0995. It's pretty easy. So basically, you just need to know m, you just need to know k, and u0 and u0 dot. With these 4 values, for sure these 2 values will determine omega n. Basically, with these 4 values, you can get the expression for the free vibration using the given expression. Okay. A little bit, we mentioned a little bit of question 10. For this system, an electronic mass is 20 kg, suspended by a spring, has stiffness, and for sure K is equal to this one. There's no doubt. Leaves 2 kg of iron scrap. So suddenly we turn off the electricity, and the iron scrap will drop down. Finally, the system, it has one mass equals to 20 instead of 22, because the iron scrap has dropped down. So the initial velocity, it should be equal to 0, because it's balanced. We just suddenly release that. Before the motion occurs, it keeps constant. So the initial velocity should be equal to 0. The initial u0 should be equal to 2 times 9.81 divided by k. It is the displacement caused by the iron scrap, not caused by the entire Is there any confusion of why we use 2 instead of 22? No question? As long as we get k, m, u dot, and u, then we can get the final expression. Okay. If no problem, let's go to task 3. The free vibration of damped system. In this case, the motion of equation equals to mu plus cu plus ku. C is not equal to 0. Okay. So before that, let's introduce one conception, which it is zeta is equal to C divided by 2m omega n. Again, the omega n is same with before. Omega n should be equal to the square root of k divided by m. And we call that C divided by C critical. C critical equals to 2m omega n. We call this one as damping ratio. This is one very important parameter. It essentially determines the behavior of the free vibration. So if we know this one, and then we introduced omega n before, it is the natural vibration, natural circular frequency for undamped system. For damped system, we have another one, omega d. The frequency is no longer omega n, it should be omega d. It has one relationship between omega n and omega d. Omega n times the square root of 1 minus zeta square is equal to omega d. And then the period of the damped system should be equal to Tn divided by 1 minus zeta square. Okay. And now let's draw okay. Let's stop here, and then as given the expression for that, ut is pretty similar, but we introduce another parameter, one exponential parameter. Okay, basically it is similar with the free vibration for damped system. You can see the second part is pretty similar. A cosine omega dt, B sine omega dt, but we are using omega d instead of omega n. Omega d, the relationship between omega d and omega n we have given. From the expression, you can imagine this part it should have bigger finger. This part, it should have one similar finger with before. And then for this expression, and for this expression, it should have something like that. So if you multiply these two functions together, we must have one final it's not pretty good. One final plotting like this way. Okay, so I just want to here I just want to show clear of the relationship between these two expressions. And now I draw another time to show it's clear for the later explanation. So I should behave like this way, and for sure the initial should be u0 and the initial slope is u0 dot, and then the period, instead of Tn, the period should be equal to Td. And we need to know the magnitude. The magnitude for the expression is decreasing. But if we draw the envelope, the initial magnitude for the envelope, it should be equal to a squared plus b squared. Then the envelope, it should be have expression that's the expression for the envelope. You can see when t is equal to 0, this expression equals to square root of a squared plus b squared. And now we give another definition is the peak value for the first vibration period, we call that U1. The second, U2, U3. So Uj is the peak value for the UI is the peak value for the TH vibrate period. Okay. And now we are going to introduce some relationship between UI. So we check the equation table. And now we finished at here. We already introduced all the parameters This is A. This is A. This is B. And now we are going to introduce these three equations, explain what this means for these three equations. It means for the first one, ut divided by ut plus td. For example, this value, and after td is this value. The ratio between these two values keeps constant. A should be equal to E zeta omega n td. And it is equal to ui divided by ui plus 1. The ratio of the peak value. So, for example, ui is equal to 1. It's equal to u1 divided by u2, or u2 by u3, or u3 divided by u4. It doesn't matter. But this value, the ratio between two peak values keeps constant. That's the meaning for the first one. For the second one, we introduced another logarithmic decrement. Logarithmic decrement. It is equal to ln ui divided by ui plus 1. This ratio, we call that logarithmic decrement. The Lagrange expression for this ratio. And then it is, roughly speaking, it's equal to 2 pi zeta if zeta is smaller than 0.3. So this expression is not very important. The following one is pretty important. So we know the definition of zeta. Zeta is equal to C divided by CR, but the relationship, another relationship we have is it is equal to 1 divided by 2 pi times G ln ui divided by ui plus G. Okay, another term, because this is damping ratio. It's very hard for us to test the damping ratio for one structure. It's not one parameter that you can obtain directly. But if we do some experiment, it's very easy to obtain the displacement value. The displacement is very easy to measure. And then if we get the values for ui and ui plus g, reversely, we can derive the damping ratio. And then we get everything like CR and CCR. Okay, now let's go to question 7. It is exactly the problem we are talking about. So there's one tank. One cable attached to the tank applies a lateral force. Lateral force, 70 kilonewton. It will pull the tank horizontally by 6 centimeters. So it means the tank deforms. with horizontal displacement 6 centimeter. And then the cable is suddenly cut, resulting free vibration is recorded. At the end of 4 complete circles, the time is 2 seconds. And the amplitude is 3 centimeter. It means that for TD, it's equal to 2 divided by 4. 4 circles, 2 seconds. So then 1 circle, we have 0.5 seconds. Okay. Then if we draw question 7. If we draw the vibration, for that, initially it has U0 equal to 6 centimeter. And then the system starts to vibrate. It vibrates 1 circle. Oh, it's not very good drawing. 1 circle, 2 circle, 3 circle, 4 circle. The time here is 2. For sure, it's 0.5, 1, 1.5. And the magnitude here is 3. And now we know the vibration. From the vibration, we can reversely calculate all the parameters underlying the system. So let's try. Firstly, the first one is calculate the damping ratio. The damping ratio zeta. We know that zeta is equal to 1 divided by 2 pi g ln ui divided by ui plus g. That we get from the equation table. Okay, the first peak value for the first natural period is U1. Second one's U2, U3, U4, and U5. So we know then it's 1 divided by 2 pi times 4 ln U1 divided by U1 plus 4. And it is 8 pi ln 2. U1 divided by U5 is equals to 6 divided by 3 is equals to 2. Then you just need to lead system is equal to 0.028. Next question is the natural period for undamped system, undamped vibration. It is actually to calculate Tn, because we know that from the experiment we get the natural period for damped system Td is equal to 0.5 seconds. And now we are required to calculate Tn, from Td to calculate Tn. We know that Td is equal to Tn divided by 1 minus zeta square. So Tn, it should be equal to Td times 1 minus zeta square. How do we get ln n in calculator? You can use calculator. Ln x means log e x. You can use calculator. I think all the scientific calculator can perform this. Now, how do we get ln U1 is equal to 6. U5 is equal to 3. From the original description, U1 is the peak value. U1 it is the peak value for circle 1. U5 for circle 5. Or at the end of circle 4, it's already the peak value for circle 5. Okay. And let's continue. ABC, and see we are calculating the stiffness. Stiffness K. So do we have the mass? I don't remember. Oh, we don't have the mass, but we have one force and displacement relationship. Okay. We have the beam when it's posed to 70 kilonewton. You have displacement equal to 0.06 meter. So U Ku equals to F. K is equal to F divided by K. K is equal to F divided by U. That's the stiffness. And the next one is we need to find the weight. The weight is equal to the mass times g. Then the task is we need to find the mass. Since we already know Tn is equal to 0.499 seconds, then omega n should be equal to 2 pi divided by Tn. 8 is equal to square root of k divided by m. This we already obtained. This we already obtained. Then it's very easy to perform the calculation to find m. So 4 pi square divided by Tn square equals to k divided by m. Then m is equal to 4 pi square divided by k Tn square. Since I made some mistake, Tn divided by 2 T omega n is equal to 2 pi divided by Tn. 2 pi divided by Tn. So sorry, made mistake. So 4 pi square divided by T square equals to K divided by M, and M is equal to 4 pi square divided by oh no, yeah. KTN square divided by 4 pi square. After we get the mass, the weight should be equal to mass times ground acceleration. Just a mass for that. And the weight, and now the damping coefficient. So we are calculate C. We have expression as the damping ratio is equal to C divided by 2m omega n. Zeta we have, m we have, omega n we have. Then you can perform. We don't have omega n, but we have Tn. It's the same. C divided by 2 times m times 2 pi divided by Tn. Then C is equal to 4 pi m divided by Tn times zeta. Let's see. And then the final one, we need to calculate the number of circles required for the displacement amplitude to decrease to 0.6 centimeter. Decreasing, it means the initial one is 6 centimeter. How many circles need when the magnitude is 0.6 centimeter? It's pretty easy also. We know the relationship we have is theta equals to 1 divided by 2 pi g ln ui divided by ui plus g. It means we have this value is equals to 6 originally, and we require this value is equal to 0.6. So you are doing is 1 divided by 2 pi g times ln 10 should be equal to 0.028, and g is equal to 0.028 times 2 pi. No. 0.028 ln 10 divided by 2 pi. This, roughly speaking, equals to 13. It means after 13 circles, the amplitude decreases to 0.6 centimeter. Is that correct? No, no, not correct. Ln 10 divided by 2 pi times 0.028. Yes. Okay, that's question 7. Basically, it's the most difficult one for today. Is there any question during this step-by-step solution? No question? For question 7, from the damping ratio calculation and the natural period of undamped system, stiffness K, the weight, the damping coefficient, and then the circles required for decreasing the magnitude to 0.6 centimeter. Okay, if no questions, let's start the final task. The forced vibration. Because Sasha only start a little bit, and I just introduced a little bit of the harmonic vibration for undamped system. We'll go deeper in the following tutorials. And one conception I want to introduce is from today's question, from question 14, only one conception need to be introduced. So when the excitation frequency it is equal to the natural frequency, it means the structure is in resonance. To spell that, resonance. Resonance. It means the vibration will go increase no bound. So release the equation of motion. The omega, it is the excitation frequency. Omega n is the natural frequency. So as long as this frequency equals to each other, it means the structure is at resonance. If we read the description of question 14, there is one n-damped SDOF system, mass and stiffness is subject to harmonic excitation at a frequency of 5 Hz. At this frequency, it knows that the response tends to be increased with node resonance. Next, wait, let's stop here. It means if we assume that original mass is m, is k, then the omega and 1, it is equals to the omega. The omega is equal to 2 pi f1. It means when we have one excitation frequency equals to 5 Hz, the natural frequency for that is equal to 2 pi times f, 10 pi. And then next, when a weight 17 is attached to the mass, 3.5 Hz. Omega n2 equals to second omega should be 2 pi f2. That's all we need to perform. And then the problem is we need to determine the mass and stiffness. For sure, we have two expressions. We have two unknowns. It's easy to solve. So, we know that omega and 1 is equal to square root of k divided by m. It is equal to 2 pi times f. Omega and 2 is equal to square root of k divided by m plus m0. In this case, m0 is equal to 17 Newton divided by 9.81 meter second square. It is equal to 2 pi times 3.5. Pretty easy. K is equal to 100 pi square. K divided by m plus m0 is equal to 49 pi square. And equation 1, equation 2. We use equation 1 divided by equation 2. We get m divided by m plus m0 divided by m is equal to 100 divided by 49. And then we get m0 divided by m is equal to m0 is equal to so m is equal to okay. We got this one and substitute the expression of the value of m into equation 1. We got k is equal to That's all. Okay, I repeat, summarize today's tutorial, and then if you have any question, you can ask. So the first one, the beam stiffness derivation, basically you are introducing EIV second order of the derivation equals to the bending moment, and then introduce boundary condition, you can find the constant for constant. And for another tab, statically indeterminate structure. That's it. And for the second one, as long as we have M, we have K, we can get omega n. And then you just need to find U0 and U0 dot. That's all. And for this one conception we introduced is the damping ratio theta is equal to C divided by 2M omega n, and it is equal to 1 divided by 2 pi g ln ui divided by ui plus g. And for the last one, we just introduced a little bit. You just need to know when the natural frequency is equals to the excitation frequency is in resonance state. That's all. Any question? Can you show the solution for task 1, another example? Maybe next time, because one of the students asked me to do that. That's why I think this example, this is not one example from the equation from lecture. I just propose this one. Maybe next time, if we have time, we can perform this one. Basically, you just repeat the solution procedure. Q is the distributed load. Q is the distributed load. I'm using Q in such a note. He's using omega, the distributed load. Like for one beam, you have distributed load. You can call that either omega or Q. It doesn't matter. Usually it's equal to 0. Okay, no problem. Any other questions? One announcement. One student asked me, can we upload the annotated notes to the system? I asked Sasha, he said no. So he encouraged you to take the notes by yourself. At least we have already all the solutions to the model you can download and taking notes by yourself. So yeah, he just doesn't allow to upload all solutions. Can we have your email address? Yes, but I'm not sure I have time to reply you. But no matter, as long as I found, as long as I got the time. Anytime when you have a question, you can put the question on Moodle on the discussion discussion sector. I think Sasha and Iman, they will reply you as soon as possible. You should also get a particular solution for. No, I cannot show you because I'm not. I answered by way your question firstly. Not answer you how it comes from, because I didn't derive that by myself. You just need to remember. You just need to remember the expression when it's at resonance. You just need to remember. It doesn't matter how it comes from. If all statically indeterminate beams should be. Yeah, for statically indeterminate structure, we should use EIV force derivation equals to minus Q. Most cases, minus Q is equal to 0 because we don't have any distributed load. Most cases, we calculate the relationship between one concentrated load and the displacement. You can see for this one, he's calculating the relationship between F and U. In this case, there's no distributed load. So he is using EIV force equals to 0. Trouble how to stack up, how should I use the initial, I guess. Let me check the equation table. Maybe I set U as one feature. Okay, I set you as one speaker. You can speak. You can talk to me now. I'm not 100% of your question. Should I use? Are you talking about this one? To be honest, I haven't go through so quick. So maybe next tutorial we will demonstrate some questions related to this. Because now his lecture only stopped before the damped system, so I didn't prepare the following one. Question 14 again. Okay. problem. Okay, by the way, maybe we discuss personally next tutorial, because I didn't prepare this. I don't know, and I also didn't get your question. I think you're Chinese, and we can talk in Chinese language. Any question? If no question, we can finish today's tutorial. Remember, practice from question 5 until question 14 for this week. No problem. No problem. No problem. Hope to see you next week. Practice more.